Okay, so this paper is titled AI Empowered Next Generation Multi-Scale Climate Modeling for Mitigation and Adaptation. It's a perspective, so a few authors together are proposing a new way to do Earth system models, serving directly the goals of mitigation and adaptation, which means it also includes climate projections, which are now being done by relatively coarse resolution models. And we often take different models for different purposes. Direct numerical simulations at one end when we want to explicitly resolve turbulence, large eddy simulations where we are focusing on impacts of eddies at some scale while modeling the eddies of smaller scale. So in that model the turbulence is not directly resolved, but they do better the mesoscale influences of the processes, let's say clouds, etc., or ocean mixing and so on. And then we have these coarser resolution global models which are used for weather prediction in one configuration, climate prediction in another configuration. Depends on what is fixed and what is coupled and allowed to evolve over time. And then we have climate projection models which require much longer integrations, so they can be even coarser resolution than climate prediction models. So there are various engineering approaches, and this paper imagines that somehow we can bring it all together and use AI to improve the models and also worry about computation, because when you do DNS and explicit turbulence resolving modeling, obviously you cannot do it at global scale. LES also is done at a regional scale, and then you have coarse resolution global models. And there's been a group in Europe, Tim Palmer, Bjorn Stevens, Julius Lingo, who keep saying that the IPCC class coarse resolution models used for projection are not really suitable for actual decision making because they are too coarse in the resolution and they don't resolve anything. They resolve temperatures at regional scales, but precipitation is not done very well, and so on. So they propose a K scale or 1 kilometer scale modeling, which should be doing all climate predictions and projections and so on. So there are many perspectives. This says Earth system models have been continuously improved over the past decades, but systematic errors compared with observations and uncertainties in climate projections remain. This is due mainly to the imperfect representation of subgrid scale or unknown processes. So when we say model has a certain resolution, it's splitting the sphere into rectangular or some other shaped boxes in the ocean, on land, in the atmosphere, and they could be, let's say, 100 kilometers on edge, which means you are saying clouds are of that order, but you can do fractional clouds as well, and so on. But basically you are not resolving the higher scale processes which are important for how the ocean and atmosphere talk to each other, how atmosphere interacts with land, and so on. So we represent those processes with some parameterization based on data and so on. So then subgrid scale and unknown processes add to the deficiencies in the way we do things. These models are amazing, as I always say, because you give it the energy from the sun at the top of the atmosphere and they do everything. They do weather, well, to some extent weather, depending on which model you are using, climate, monsoon, El Nino, Pacific Decadal Oscillation, and so on and so forth. So mainly the idea is that they propose a next generation Earth system modeling approach with artificial intelligence that calls for accelerated models, machine learning integration, systematic use of Earth observations, and modernized infrastructures. The synergistic approach will allow faster and more accurate policy relevant climate information delivery. We argue a multi-scale approach is needed, making use of kilometer scale climate models and improved coarser resolution hybrid Earth system models that include essential Earth system processes and feedbacks, yet are still fast enough to deliver large ensembles for better quantification of internal variability and extremes. So lots of technical terms, you either know them or you will get confused, but basically internal variability is natural variability. I mentioned El Nino, monsoon, Pacific Decadal Oscillation. These are not directly related to climate change. They are happening internally because of the nonlinearities and the interactions between atmosphere and ocean, for example. And you need ensembles because Mother Nature goes in some direction, but we don't know where she's going to go. So we make an envelope of realization saying Mother Nature could take any of the paths between these two edges. So that gives you a sense of what are the possible evolutions that is necessary to understand what could happen, because you cannot make deterministic predictions saying Mother Nature will follow exact this path, right? Small things can make things, evolution of climate go in a very different directions. We've talked about it elsewhere. If you understand, fine. Otherwise, don't worry about it. Okay, so together these can form a step change in the accuracy and utility of climate projections, meeting urgent mitigation and adaptation needs of society and ecosystems in a rapidly changing world. So mitigation's goals are, of course, to avoid the unmanageable, in the sense we want to reduce our impact on the climate and the planet, and hence we want to do mitigation of, we are reducing emissions, renewable energy, electric vehicles, bioenergy, and all those good things, including technology, carbon capture, and so on. And adaptation is managing the unavoidable things that are already here, and we have to deal with them, whether it's extreme events, health impacts, agricultural impacts, water resources, and so on and so forth, right? So this is a perspective, and they imagine these things in a certain way. And the idea of doing an Earth system model is that there are indeed feedbacks without which you will never get a proper representation of the climate, which is what you will try to predict, but also impacts. So here you have the components like radiation, terrestrial carbon cycle and phenology, land-atmosphere interactions, wildfire, and you have hydrological processes, permafrost, carbon, climate feedbacks, and so on. So these are Earth system feedbacks and processes enhanced with machine learning, which means you have somehow improved your data system, or you already assume there is enough data to learn from observations to help models to better capture these feedbacks, which the models may not be able to do by themselves. So there is incoming solar energy, you have all sorts of clouds, and you have precipitation and evaporation processes, soil moisture, etc. You have vegetation and ecology. You also have snow cover and transition from solid to vapor, so sublimation processes. You have topography, reflectivity, and you have lakes and rivers also involved in hydrological processes. You have natural wildlife as well as human managed livestock, and so on. And you have evaporative and heat energy exchanges, outgoing thermal energy, aerosols, which are very tricky to do, cirrus clouds, cumulus clouds, various types of clouds, stratus again here. So clouds, convection, and microphysics are involved in the atmospheric side. The gravity waves and turbulence are needed to couple the, let's say, stratosphere and the troposphere. There is evidence that you need them to do things correctly. So atmosphere has temperature, winds, precipitation at a simple level, and there are many other processes. Salinity, heat, and momentum exchange in the ocean. Ocean model sits here, talks to the atmosphere model. In the ocean, you have ocean dynamics and cryosphere, sea ice, etc. And ocean currents, temperatures and salinity. Marine biology is, of course, important. Realistic geography and ocean bottom topography. So basically it's a very motherhood statement of how many feedbacks there are, and the main message is that the coarse resolution models tend to miss these, and many of them do not include explicitly human influences and land uses. So human influence comes through fossil fuel burning, emissions, production of aerosols, and land use causes changes in the topography, in the interface that the atmosphere sees, changes the runoff as well, and groundwater storage, soil moisture persistence, all kinds of feedbacks are there. So feedback mechanisms across the Earth system introduce uncertainties in climate projections affecting carbon cycles and climate change responses. Essentially, we are doing integrated assessment models, which are kind of a socio-economic models which assume technology, choices in energy and transportation and policies, and give you pathways of emissions going into the future for various scenarios, as we call them. You can look them up elsewhere on my channel. And you feed that to an Earth system model or a climate model. We'll use them interchangeably here. And Earth system model will produce climate, and in the climate you also compute carbon cycle. Some will not allow a feedback between carbon cycle and climate, and some will allow, so that's why we are mentioning here also terrestrial carbon cycle and phenology. There is also ocean carbon cycle and marine ecosystems that is not explicitly mentioned here, and so on. Okay, so climate modeling for mitigation and adaptation, according to them, is climate and Earth system models provide a fundamental source of information for climate mitigation and adaptation decisions. Applying these models to understand climate change and to provide multi-model climate simulations is internationally coordinated by the World Climate Research Programme's Coupled Model Intercomparison Project, CMIP, with simulations of the most recent phase, CMIP 6, just being completed, 21-22. CMIP has supported the climate research since the early 1990s, while careful analysis of CMIP models' output has provided a fundamental basis for Intergovernmental Panel on Climate Change assessment reports and climate policy negotiations over the past several decades, such as the Paris Agreement. However, due to their complexity and computational costs, ESMs or Earth system models typically have a coarse resolution of the order 40 to 160 km, depending on which model it is, because some can have fewer biogeochemical carbon cycle components and higher resolution. Some can have more details of the Earth system processes, but coarser resolution, often optimized for computational efficiency, because these are long integrations and you need to do multiple scenarios. These models still exhibit systematic errors compared with observations, and large uncertainties in their projections remain, such as on precipitation changes, the jet stream and the ocean circulation changes, etc. These climate projection uncertainties may deter policy decisions regarding adaptation, investment, security and resiliency. Climate mitigation and adaptation decisions could benefit from more reliable projections of the Earth system, not only globally but also increasingly on regional and local scales where adaptation and resilience take place. So adaptation really requires hyper-local information, region-specific information, and often we do this now by using downscaling approaches, as we'll see in the schematic in the next slide. Different mitigation pathways involve strategies that differ in when they achieve net zero emissions and vary in the direction of mitigation efforts between short-lived, as they say in the US, and long-lived climate forcers, reliance on land use strategies, and the scope and timing of carbon removal. So all of them rely on carbon capture and sequestration. Therefore, ESMs must depict coupled cycling of greenhouse gases encompassing both natural processes and human-induced influences for a broad range of policy-specific scenarios, which is discussed in detail. I will skip that because I have covered it elsewhere. In this perspective, we call for a hybrid multi-scale Earth system modeling approach, bringing the artificial intelligence revolution to climate modeling. Machine learning provides great potential to improve some of the limitations apparent in coarse resolution ESMs and high resolution global kilometer scale climate models. Our proposed approach provides the potential for a step change in model performance and climate data utility, while bridging across the scales and process complexity, as well as utilizing the full hierarchy of models. So they are not advocating one model doing everything. They are saying we can keep all the models, we just make them talk to each other and exploit the best properties, characteristics and abilities of each model. As we said, ESM coarse resolution models will capture the feedbacks that are very important. K-scale models will do the physical climate very well, let's say, and then DNS and LES will do some clouds and ocean eddies or something and feed into the process, and AI is helping improve the processes and so on. So here is the schematic of the proposed AI-empowered multi-scale climate modeling approach for urgent mitigation and adaptation needs. This approach bridges across scales and processes. This approach bridges across scales and process complexity for faster and more accurate climate information, also on regional and local scales. We note that large eddy simulation or LES and Earth observations are also used to directly refine kilometer scale climate models and coarser scale ESMs. DNS, direct numerical simulation models, are mentioned here. Basically, DNS explicitly resolves turbulence, whereas LES parameterizes turbulence at very small scales. It focuses on larger eddies, which are still very important but are not captured even by kilometer scale models, because eddies happen at much smaller scales, especially at higher latitudes and so on. So here are Earth observations which are improving, and there is always separate issues about sustaining them, the coverage, ocean, etc. And they are talking to each other here, DNS into LES into kilometer scale models, which is already happening in Germany and I think maybe in the European Center, and Earth observations are already being assimilated for climate prediction, weather prediction and so on. But here we are imagining then using that also for hybrid physics plus machine learning Earth system models, and imagine to be doing different things. And you can imagine that they are then talking to machine learning downscaling and regional refinement, which is what typically is done. So even if you get a kilometer scale model, the output will be so much that you will need to use AI/ML to get bite-sized patterns and information out of it. So you are going to somehow combine all of them to do impacts and then provide reduced systematic errors and more accurate climate projections co-produced with users for actionable climate science. So some products may go directly from kilometer scale climate models to here, and they may also serve impact assessments, whereas some others will go through these routes here to regional downscaling and serving climate services needs or adaptation, resilience and mitigation needs. That's how it's imagined to bridge across scales. So higher resolution with new computing opportunities, improved with physics aware machine learning models, constrained and benchmarked with Earth observations, modern and operational science infrastructures. There are many details. They talk about how the hardware can be best exploited by doing this and so on and so forth. Okay, so then reading a bit more about an AI empowered approach for faster and more accurate hybrid climate modeling. So this is the hybrid modeling where you are using basically everything, whereas K-scale modeling is not talking about talking to other models. It's just saying these models will never get it right, so we must do this. But then these people are here in this article saying we need to keep these because they do the feedbacks better than the K-scale models, because K-scale models do not explicitly represent everything, just for computational needs, let's say for now. Okay, so we argue that a holistic approach to climate and Earth system modeling that fully integrates AI will be a productive path towards productive path forwards to make progress in climate modeling. Our proposed approach we just saw is based on 4 pillars: higher resolution across scales with new computing opportunities. Next generation climate models and ESMs need to fully leverage modern and evolving hardware to enable simulations at higher resolution that better resolve important processes such as deep convection in the ocean or ocean eddies. Convection also happens in the atmosphere. Given the shortcomings of even high-resolution simulations and the continued need for coarser ESMs to represent Earth system complexity or the feedbacks that we talked about, this needs to be complemented by the second pillar, hybrid ESMs improved with physics-aware machine learning, where parameterizations or sub-components of the models are replaced with ML to improve the representation of sub-grid scale processes or poorly known physical and biological processes. So in the coarse resolution ESMs right now, we just parameterize a lot of things, whereas physics-aware ML can improve that by directly representing the processes captured by ML from data. Okay, that's physics-aware ML. The third pillar then is to harness the wealth of Earth observations to evaluate, constrain, calibrate, and improve models. This needs to be supported by the fourth pillar, which is modern and operational science infrastructures to define common experiments and standards to provide annual updates of climate forcings and climate feedbacks that relate forcings to the Earth's energy imbalance, and to operationalize policy-relevant climate model simulations and outputs, including regionally downscaled or regionally refined output. Okay, so basically, at least in the perspective, words are there to cover everything. Exactly how this will happen obviously depends on who's going to put the human, computational, and financial resources behind this, and whether we'll have one model, one such hybrid framework for the whole world, or we will again run multiple models like we do in CMIP, right? CMIP 6 has a bunch of models from every country. An important component of this approach is that coarser scale ESMs are enhanced to hybrid models in which parameterizations and subcomponents are improved with ML informed by kilometer scale climate model simulations, or even high resolution large array simulations and direct numerical simulations, and by Earth observations. So some full integration of AI is going to happen through these multi-scale modeling. Hybrid ESMs promise to have substantially reduced systematic errors and enhanced projection capability compared with current ESMs. In contrast to kilometer scale climate models, ESMs incorporate important Earth system processes and feedbacks, as we saw, while still being fast enough to provide large scale ensembles important to simulate internal variability and extremes, and to improve attribution and understanding. These models can be brought to actionable climate scales using ML-based downscaling or regional refinement that can also be used to drive impact models, which are needed often for loss and damage to determine what caused what and who's responsible for what and how to compensate for them and so on. Maybe insurance, reinsurance, or maybe International Climate Fund and so on. They can themselves be increased in resolution through new computing opportunities, since even kilometer scale climate models still require parameterizations of even smaller scale processes, and for processes that are not likely to improve just through increased resolution, such as land and cryosphere, they can also be enhanced to hybrid kilometer scale climate models using this same approach of AI empowered processes. We argue that modernizing infrastructures are required that utilize AI towards the operationalization of policy relevant simulations and model outputs to a broad range of stakeholders. This approach could substantially enhance the applicability of climate modeling and projections also on the regional to local scales to tackle urgent mitigation and adaptation needs. It requires co-production as indicated with the handshake in figure 2, which is this one, co-production. We all use this terminology now. So it requires co-production as indicated with the handshake in figure 2 with stakeholders that ensures that services utilize the most advanced capabilities available, while the scientific community promptly addresses any service gaps. So instead of just doing modeling and providing output, we also are aware of, oops, it's quite long here, so I'll probably reduce the text. Anyway, so higher resolution across scales with new computing opportunities, which we mentioned. Infrastructure has to evolve to understand this framework of going from DNS to LES to kilometer scale to ingesting data and coarse resolution system models with feedbacks and so on. So hybrid ESMs improved with physics aware mixed layer, machine ML in oceanography is mixed layer, so I always keep saying mixed layer by intuition. It's machine learning. So machine learning can also be used to replace parameterized processes that do not have a clear physical basis and that are still unresolved in high resolution simulations such as warm rain or ice microphysics, photosynthesis, vegetation phenology, or land atmosphere or ocean atmosphere interactions, as long as sufficient Earth observations are available. So this is key. Any AI and ML you want to do requires data, because these are data driven derivations of knowledge that we were simply parameterizing statistically, but this physics aware ML can only work when you have a lot of data. Sometimes models are used as well, but I don't want to go in that direction. So hybrid approaches are not without limits, and several machine learning challenges need to be overcome. So ML struggles with extrapolation beyond the training regime, which is always the case. New approaches to improve those predictions, such as by incorporating climate invariant variables or multi-fidelity approaches that merge traditional parameterization with ML trained on historical data, are showing promising progress. So that's kind of a detail that I won't go into. Jumping ahead to conclusions, large standing systematic errors in coarse scale ESMs have motivated the development of kilometer scale global climate modeling efforts with the goal to provide more accurate near-term climate predictions. So K-scale is right now going for near-term, which could be multi-year to decadal also, not just seasonal or intraannual. However, these models are too expensive to be run on century timescales and are often limited in their representation of the complexity of the Earth system complexity. This is true, as we already said. Climate projections with coarser ESMs that comprehensively simulate emerging Earth system processes and feedbacks that we looked at will continue to be required to reliably project the long-term forced climate change response and extreme events in the face of intrinsic climate variability. However, a step change in models' performance is required. I'll skip some text and jump here, but I'll make one point before. When we go to K-scale models, they are not necessarily capturing all the carbon cycle, vegetation, dynamics, and so on. They are focusing on physical climate to be captured by increasing resolution. But Earth system feedbacks are important because they need to be explicitly represented. So what we don't know is whether including those feedbacks at coarser resolution actually can give us a better answer than neglecting those feedbacks and going for higher resolution. So that's a tricky thing to explore as well. To achieve this vision, the international community must tackle several challenges on the machine learning side: the algorithmic part, operationalization of policy-relevant simulations enforcing, and the broad and inclusive accessibility of climate model data as we outline here. Challenges lie ahead, but this objective has never appeared to be as much within reach as it is today. We believe that the debate of future modeling should not be centered around high-resolution climate modeling versus complex, coarser resolution ESMs. Instead, a new ML-empowered multi-scale climate modeling approach that integrates Earth observations through modernized code, hardware innovations, and adaptive international science infrastructures is required. So it is imagining a single model framework, or a single framework that includes all the models. So how the workload will be distributed and how the inputs and outputs will be shared, etc., is some separate issue. Indeed, we argue that climate modeling needs to be approached within a hierarchy of models going across complexity and resolution, ranging from high resolution to coarser ESMs that are enhanced with machine learning and downscaled or regionally refined to drive impact models as described in this perspective. This way, we will be able to better project the full complexity of future Earth's climate and extreme events at unprecedented accuracy, also improving climate information and technology assessments for sustainable developments of sectors such as transport, energy, and aviation. I'm surprised they don't mention agriculture and water and health. It's incumbent on the whole Earth system modeling community to join forces to offer the best and most accurate climate information for urgent mitigation and adaptation needs in a rapidly changing world. Time is of the essence. Well, right now climate and weather models are done by each country, sometimes multiple centers within the same country. And IPCC, CMIP's coordination is done globally, but each country is running multiple models and their outputs are brought together. They all follow the same protocol. So you have to be clear whether such multi-scale modeling from DNS to K-scale to ESMs will be done as one big system run across the world, or there will be multiple systems. That's not clear totally in the perspective, but you can imagine that it's best done as one big framework where everybody is coordinating at global scales, or all communities across the globe are cooperating and coordinating into one framework. Okay, let's leave this here for now.